The difficulty with what we have done so far is that we are limited to solving first-order differential equations or stuff we can rearrange to be first-order equations. Like we did that reduction of order problem where we took a second-degree differential equation, did a substitution, and ended up with a first degree. If I want to think about linear equations in general, I really need to understand what's going on with higher degree equations. And this is the key to get there from here. So let's go back to the start. An nth order linear initial value problem means I'm going to have some function of x times the nth derivative of y plus some other function of x and minus first derivative of y all the way down and then this is going to be equal to some g of x. That's our general differential equation. And if I give you an initial value problem, then I'm going to have a condition on all of the derivatives except the highest. Please notice that these all occur at the same x value. Now, for a first order differential equation, that meant we knew y0. And that meant we knew we had this differential equation and it went through this point. If I have a second order differential equation, then I have two initial conditions. Those two. A condition on y and a condition on y prime. Wait a minute. If I'm dealing with a second order differential equation, then I have some point that's new. I have a point x0, y0 that's given by this. What does this condition tell me about what's going on at that point? This condition says that there's a y value at x0. What's this condition Tell me. But not only, we have a slope there, right? So not only do I know we go through that point, I know we go through it with a slope that's given by my initial condition. If I were looking at a third order differential equation, I'd have three initial conditions, right? The second one would tell me about concavity here, and so on. I can look at these like I'm looking at a power series, and what we're really seeing are the coefficients in that power series. But the fact that all of these conditions are at the same x value, that's our initial value part.
Yeah, exactly.
Yes,
That's good.
absolutely required. I was looking like a rag mom.
Good.
Thank you. Now let's think about all of these functions a n minus 1, a2, a1, a0. Those are all the coefficient functions. I forgot to write of x up here. a0 of x. Oops. I need all of those a functions, and I need this g function. And I need them to all have something in common. And hopefully, it's something in common at this point in question. So here is what I think is the big theorem. Let's have all of these functions be continuous on some interval I. And I need an to be not zero there. If my initial value point is in I, then our differential equation has a solution, and it's unique. But that solution is only unique on the interval in question. So let's take a look at an example problem. Now, the big problem I have to start with this initial value problem is that I have absolutely no idea how to solve it. None whatsoever. But before I go about solving it, let's think about the conditions in my theorem. I have an A2, an A1, and an A0. What are the functions A2 of x, A1 of x, and A0 of x. Please tell me I get to answer that. Not with an alarm. Oh, well.
X squared negative x.
Almost. X squared, negative x. What's the coefficient of y? Just 1. The g of x function is 0. Because that's the other side. Now, where are these functions continuous? Everywhere. They're polynomials. They're continuous everywhere. According to my big theorem, I need the interval to be where these are continuous and where an is non-zero. Where is an equal to 0? In this case, that would be A2, because it's second order differential equation. It's only equal to 0 at 0 itself. Which means the interval in question for this problem is either x less than 0 or x bigger than 0. Now, looking at our initial value is at what x value? At 1. That means I want to use the interval from 0 to infinity, because those are y of 1 and y prime of 1. That means I must have a unique solution to this problem on the interval from 0 to infinity. Well, it turns out that function works. How do you know I'm not blowing smoke in your ear? I claim this is a solution. I could be talking. How do you know I'm not talking? Oh, all the time. All the time. But the easiest way is to check. What's y prime? What's y double prime? C and 1 and C2 are constants. What's y prime? It's time for the product rules. X times 1 over X is just 1, so I distribute the C2 through, and I get this. What's Y double prime? Great. Now let's plug that into our original equation, make sure it works. X squared Y double prime minus XY prime plus Y. What do I get? If I don't get 0, we have a problem. I claimed it was equal to 0. Let's plug in and find out. X squared times C2 1 over X minus X times C1 plus C2 plus C2 ln X plus the original Y, C1X plus C2X ln X equals. Algebra simplifying. Here I'm going to get X times C2. Here I'm going to get minus C1X minus C2X minus C2X ln X. And then down here on the bottom, I have a plus C1X and a plus C2X ln of X. Please notice, wonderful things happen. This cancels with this. This cancels with this. And this cancels with this. It is 0. I now know this equation is a solution to my differential equation. Does it satisfy my initial values? Oh, I don't know yet. I should find whatever constants are going to work, right? That's what we do when we do the other ones, right? You give me an initial value, I plug it in, and I get the C's. I got 2 C's. How many things do I have to plug in? I better have 2 or we're deep. So, what were my initial conditions? Y of 1 equals 3. All right, wait a minute. If Y of 1 equals 3, that's Y. C1 times 1 plus C2 times 1 ln of 1. And then Y prime of 1 was equal to -1. But this is my expression for Y prime. C1 plus C2 plus C2 ln of 1. What's ln of 1? Well, that makes this top equation C1 plus 0. Wait a minute, that's equal to 3. I just found C1. Now I can go back down here and I can say, hey, that means this is 0 as well. C1 plus C2 equals -1. So 3 plus C2 equals -1. That means that C2 is -4. We found the unique equation that satisfies our initial value problem. This is the only curve that goes through the point 1, 3 and has a slope of -1 at that point that satisfies this differential equation. in general, if I have multiple initial values, this was a second order differential equation, so I had two of them. I'll have a 2x2 system. I'll have an n by n system in general. What am I going to use to solve my n by n systems of equations? I don't know. It's the easiest way to solve n by n systems of equations. Oh, matrices from linear algebra. Questions? You didn't think we could forget all that now that we're in a different class? We need it all. The hypotheses that my functions are continuous on the interval in question, and that an is non-zero on that interval are required to guarantee uniqueness. Page 121 has an example, I believe it's example 3, of one that isn't unique. If our conditions are not all at the same x value, we no longer have an initial value problem, we have a boundary value problem. If we have a boundary value problem instead of an initial value problem, we have boundary conditions instead of initial values. So what? Well, it is possible that a boundary value problem can have different solutions in spite of the uniqueness ideas that we talked about in theorem 4.1. Here's an example. This differential equation, y double prime plus 2y prime plus 2y equals 0, is solved by the ugly ass equation, y equals number e to the x cosine of x plus number e to the x sine x. This is related to complex numbers and integration by parts. Here's the deal. Find y prime and y double prime for me. We're going to need them. Actually, no, yeah, find them both. Y prime and y double prime. You'll need to do a little algebraic simplification because you'll need to do the product rule a bunch. Y prime is C1 times e to the x cosine x. The derivative cosine is minus sine C1 e to the x sine x. Over here, I get C2 e to the x sine x. The derivative of sine is cosine, so I get C2 e to the x cosine x. If I group those, that's C1 plus C2 e to the x cosine x plus C2 minus C1 e to the x sine x. I'm going to have to do the regrouping another time to do y double prime. Take the derivative of e to the x, you get e to the x. C1 plus C2 e to the x cosine x plus C1 plus C2. Derivative of cosine is minus sine. There'll be a negative here. E to the x sine x. Derivative of sine is cosine. The derivative of e to the x is e to the x plus C2 minus C1 e to the x sine x plus C2 minus C1 e to the x cosine x. These are my cosine pieces. What happens here when I combine those? I'm assuming it means you're full. What happens when I combine these? C1 plus C2, C2 minus C1, the C1s cancel. 2C2 e to the x cosine x. What happens here with the e to the x sine x terms? So yes, I'm very happy a bunch of canceling happens. Now, if you push it, you'll notice y double prime doesn't have a 2. Y prime does have a 2. Y has a 2. And those 2's are going to cause all the canceling to happen in the right place. So we could take y double prime plus 2y prime plus 2y, sorry, minus 2y prime plus 2y, and show that this does work as a solution. Here's a boundary condition, or an initial value. Let's do this. A. If I tell you y of 0 is equal to 1 and y prime of pi is equal to 0, you should be able to solve for C1 and C2. Please do that. Y is up there at the top. Plug in 0, set it equal to 1. See if you can give me a C1 or a C2. Same thing with y prime. That's this right here. Plug in pi. See what comes up. The first thing I'm going to ask you is, does any of this get any nicer when I plug in 0 and I plug in pi? Okay, so y of 0, what do I get that makes that nicer?
C2 times that's all.
Great, so that means I only need this. What's e to the 0? What's cosine of 0? Hey, I found C1. I can use that in the next part. What's cosine of pi? What's sine of pi? So that piece is gone, and I have negative C1 plus C2 e to the pi is 0. But you just told me up here that C1 is equal to 1, so that's 1 plus C2 e to the pi is equal to 0. What's C2? -1. I found a unique solution because I had initial values. They were, I don't have initial values, those are boundaries, right? One at 0, one at pi, one for y prime. It worked. I got a unique solution. Try this set of values. Y of 0 is 1. Y of pi is 0. Not y prime. So my boundary values, because they're at two different x values, are now both about y. And if you think about it, that means I'm actually saying, I want you to go through two different points with this curve. As opposed to, at this point, have a particular slope. I want you to go through these 2 points. Well, now, do the same thing. Find me a C1, find me a C2. But these are both about y. So if I plug this in, I have C1 e to the 0 cosine 0 plus C2 e to the 0 sine of 0 equals 1. If I plug this one in, I have C1 e to the pi cosine pi plus C2 e to the pi sine pi equals 0. Again, let's simplify as far as we can. Cosine of 0 is, sine of 0 is. Same thing over here with the pi's. Cosine of pi is, sine of pi. So this is 0, this is 0. This tells me that C1 is equal to 1. This tells me C1 times e to the pi with a minus sign on it is equal to 0. The only way that's going to work is if C1 is 0. In order to try and satisfy both of these boundary conditions, I need C1 to be 1 and 0 at the same time. Can you do that? Oh, hell no. This has no solutions. It is even possible to end up with a boundary value problem that has infinitely many solutions. If I tell you that I want you to try y of 0 equals 0 and y of pi equals 0, hang on a second. C1 e to the 0 cosine 0 plus C2 e to the 0 sine 0 equals 0. C1 e to the pi cosine pi plus C2 e to the pi sine pi equals 0. We know that this is 0. We know that this is 0 from the sine and the cosine. Over on the left, what does that tell me the value of C1 is? Zero. What about on the left? On the right? It's also 0 because this is number times -1 times C1 equals 0. The only one that's going to work is C. Hey, wait a minute, that's the same. This is a good thing. Except, what do I know about C2? Not in this case. In this case, I know absolutely nothing about C2, unfortunately. There's been none of our conditions have told me anything about C2, right? Which means as far as C2 is concerned, C2 is a free variable. Gee, that sounds familiar, like linear algebra. I did not actually have any value of C. C2 is free. Any value y equals C2 e to the x sine x for any value of C2 is a solution. Which means we don't just have one solution. We don't have no solutions. We have infinitely many solutions here. Again, I'm stuck back in linear. I have a system of equations that either has one or none or infinitely many. Here's an infinitely many case. In spite of the fact that the functions we were using were continuous everywhere, the coefficients were 1, -2, 2, and the g of x was 0. They're continuous everywhere. The first A2 is non-zero everywhere. This is going to be valid everywhere. Theorem 4.1.1 only says I have a unique solution if I'm doing an initial value problem where they're all at the same x. These are at two different x's. I can have infinitely many solutions. I could have no solution. Boundary value problems have more latitude to them. Questions? I keep hearing an awful lot of terms that I used in linear. Free variable, infinitely many, simultaneous equations. This sounds a lot like linear. So let me go back to my linear class for a minute. And remember that when we were setting up equations, we almost always wrote them the same way. Number x1 plus number x2 plus number x dot 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 equals thing. Number on the other side. And the easiest ones, when the numbers on the other side were equal to, what did I want the numbers on the far side to be if they were all going to be easy to deal with problems? Back in linear. 0. And we called those somethings. We gave them a name. Unfortunately, no, but that's definitely what you talked about in complex this morning. McNabb was telling you about it. Not only have we called it that, we used it again here in this course just yesterday to mean something different. So I'm going to use the same word to mean two different things. We talked about a function being homogeneous of a particular order. A set of equations is homogeneous if the right-hand side is 0. So this is a slightly different idea about the homogeneous functions. If the thing on the right is not 0, it's not homogeneous. But it turns out that when I'm dealing with differential equations, it's always, always, always easier to start with the one that equals 0. If I ever want to solve an equation where the right-hand side is not 0, I always start by solving one where the right-hand side is 0. I only change the right-hand side. That's what makes it the corresponding homogeneous equation. It's the same left-hand side. So consider the one we were just looking at. Y double prime minus 2y prime plus 2y equals 0. That's a homogeneous equation. Once I know how to solve this, I can then solve something like that. But I can't solve this one directly without solving that one first. I can't solve the non-homogeneous one before solving the homogeneous one. So I'm always going to start with the assumption that I'm working with the right-hand side being 0 to begin with. Okay. I'm going to make the same two assumptions I made for my initial value. On some interval I, we assume all of the AI of X functions and G of X are continuous. If that G of X is 0, I'm not really worried about it for right now, but in general, I want to do that. And that my leading coefficient function is not 0. If I don't have these, we're screwed. Okay. I've been using y prime, y double prime, y triple prime, all of these things. I want to change my notation just a little. Well, what's our other notation for derivatives instead of y prime? The dy dx notation. I want to think of this as an operator on y. So this is a thing you do to a function. We will see frequently in this textbook. We will write this as a function of a function. So I'll write capital D of y. That means take the derivative of this thing. Just a new notation. But the best part about this is stackable. My second derivative would then be d squared. My third derivative is d cubed. I like writing d cubed more than I like d3y of dx to the third. That's atrocious. Wait a second. If that d squared y means the same thing as y double prime, then I could think of this as an operator. It operates on function. You give me a function, the d tells me what to do with it. Differentiate. As many times as it says. I think it's chapter 7, but I know it's mentioned in chapter 1 in the linear book. We thought of a matrix as a linear operator. I want to use operator the same way here. Operator. Linear can mean combinations, right? We talked about linear combinations of things. So here is a linear combination of operators. This is operators. That means it needs to act on something. It needs to act on a function. And this is a derivative, right? When you take the derivative of something and the thing is added, you just add. You take the derivative of something and it's subtracted, you just subtract. Which means this operator can distribute. Okay, first question. D of y means? And d squared of y means? Which makes this y double prime minus 2y prime plus 2y. The expression up here is an operator version of my differential equation. Take the second derivative, subtract 2 times the first derivative, add 2 times the function. As a matter of fact, this is an operator that is linear under the definition we used for linear. D of a constant times the function. That's the constant multiple rule from taking derivatives. And the derivative of a sum is the sum of the derivatives. I'm pretty sure that's chapter 1, section 6 or 7 in the lay book from linear algebra last year. D is a linear operator. In exactly the linear algebra sense. Since it is a linear operator, I am going to use capital L for a shorthand. Notice that looks exactly like our differential equation, only instead of y's and y derivatives, I now have d to the n and d to the n minus 1 all the way down to d. And then on the end, I have nothing. That's an identity. Our initial value problem can now be written as a very simple thing. L of y equals 0, or L of y equals g of x. The one on the left is homogeneous. The one on the right isn't. And that represents a differential equation. Now I can stop writing out that gargantuan big initial value problem crap over and over and over and over again. I can just write L of y. This is just a notational change. But the reason for this notational change is for me to understand how the things I learned in linear algebra still apply to this course. Now, the best part about the fact that I know you all took linear already is that I go on and say one more important thing. We learned, oh, I'm standing right in the middle of the equation. We learned that if you had a vector that worked, you had another vector that worked, you could combine them, right? To get a solution to a matrix. If you had one vector that worked, another, matter of fact, if you had a whole set of vectors, you could build all of your solutions out of them. What did we call such a set of vectors? A way to build my solutions out of these pieces. No, and now's where we use that word.
Orthogonal.
An orthogonal what?
Matrix. No.
No, but you're close. I'm talking about a collection of vectors.
Series. Oh, God.
No, don't just start throwing stuff at the wall. We'll see. I know this word is in your vocabulary. A basis. An orthogonal basis. We had a basis of vectors. And that collection of vectors had a really nice property. We had exactly the right number to cover everything we wanted to cover, and the vectors were linearly something. There's an adjective there. Search your memory banks, undump the file, go back in your time machine, restore the sucker. An adjective. Vectors were linearly something to make a basis. One of the two. They were independent. So I would like to create an equivalent idea here. So let's suppose I have a group of functions, y1, y2, all the way up to yk. And they're all solutions on some interval to our differential equation. Then the function c1y1 plus c2y2 plus cky is also a solution to L of y equals 0, where C1, C2, dot, 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 CK are constants. A linear combination of solutions. Back in linear algebra, we called this the superposition principle. What I'm really saying is that if I have some building blocks, y1 through yk, then I can use them to build another solution. But it would be nice if my blocks were all different from one another. In vectors, we talked about whether or not they pointed in the same direction or pointed in different directions. And that was what we meant by linear dependence, Mia, was that they pointed in the same direction. And I didn't really need both of them. I only need one vector to point in any given direction. Definition. A set of functions f1 up through fn is linearly dependent if there exists some set of constants C1 up to Cn, not all 0. So that C1F1 plus C2F2 plus dot, 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 plus Cn Fn equals 0 on an interval. If the only set of constants that make this work are all 0, then my functions are linearly independent. with the exception of using the word function instead of vector. This is the exact same definition we used in linear algebra. As a matter of fact, I think we wrote it. My vectors are linearly independent if that equation equaling 0 up there at the top of the screen only had the trivial solution C1 equals 0, C2 equals 0, all the way up to Cn equals 0. So here's a question for you. Is this set of three functions dependent or independent? Why?
Just look at the constants. There's some the expression equals 0 or C equals 0, C is functions that kind of so it's C15 or C.
Say again, no, the C15 makes.
But when I saw 5, that's why I said if I saw something.
But if I set C1 equal to 0, is the way to make the rest of these not 0 and have it still work?
If you get C1 0,
Or if I make, even if I make C1 not 0, then is there a way to make this work where C1, C2, C3 are not all 0? Any one of them could be non-zero, or some combination, maybe even all three, will be non-zero. So I need to know what it is. If you are correct, we should be able to find one where this is equal to 0. Hang on a second. Two of my favorite functions are in here, cosine squared and sine squared. What happens when you add those together? You get 1. So what if I said 1 times 5 plus -5 times cosine squared plus -5 times sine squared? What's that equal to? Well, this is a 5. This is -5 times cosine squared x plus sine squared x. And you just told me that was equal to 1, which makes this 5 minus 5, which makes this 0. These are dependent. Another way to think of this is that there's a way to write 5 as a multiple of cosine squared and sine squared, isn't there? 5 cosine squared plus 5 sine squared gives me 5. And again, this is the same definition we used to talk about linear dependence of vectors. If a set of vectors is dependent, then there's a way to write one vector in terms of the rest of them. But we had a test back in linear. I could look at a set of vectors and I could do something and I could say this set of vectors is independent. This set of vectors is dependent. Here are three vectors. How do I know what tests can I do to see if these three vectors are independent? There's an easy way and a hard way.
Maybe something equals even reduce
Yes, and that is the long way to do it. I take C1 times the first vector, C2 times the second vector, C3 times the third vector. I get a set of equations, and I do reduced to echelon form. Let's start that setting. Since I'm doing vectors, the zero vector is what goes on the right-hand side, which gives me the following set of equations. But you just said I was going to do reduced row echelon form, Mia. What do I do reduced row echelon form on? I would do row operations on something. On what? I would do the Gauss-Jordan procedure. That's my reduced row echelon form, right? But I would do it on a matrix. The matrix wait a minute. That matrix has as its columns those three vectors. The big, huge, monstrously often used, the most commonly used theorem in all of linear algebra. This has only the solution x equals 0 if this matrix is unfortunately the independent, and there is a single number I can calculate to tell whether or not that is independent or dependent, whether or not it is invertible or not. Yes, Noah, we did that last fall. I know we did it. How do you know if a matrix is invertible?
It's like determinant. Yeah.
There's the magic word. I take a determinant. Okay. I take a determinant. I want to take a determinant with these things. I need to translate this exact idea of doing a determinant. By the way, the determinant of this matrix is 6. It's upper triangular. So the real question that I need to ask is, what is the function equivalent of a determinant? How do I do this with sine and cosine and x and ln and e to the x and all the rest of that garbage? But I've just run up against the clock. So that is where we'll pick up, not tomorrow. Because tomorrow's the exam, not Friday because we have the class off. That's where I'll pick up on Monday. So I will see you all on Monday. I'll see you tomorrow for the exam first, and then see you Monday for the rest of this. All right? Have a wonderful rest of your day.